So, good afternoon, everyone. So, I'm here to talk about something which might sound a bit weird for people who have worked on high throughput data systems. So, we we at RudderStack handle 100K events per second on a daily basis, and the underlying software which handles this is neither a message broker like Kafka or Pulsar or a custom message broker, but we do all of this under using Postgres. Now I'm here to talk about things which nearly broke and the things which we did to sort of fix this and make this system work while we had this journey of 5 years of reaching this scale of a real-time data system using RudderStack. So this is a war story, and I'll just share some insights of whatever we have went through while building such system in the last 5 years. So quick introduction about myself. So I'm Rohith. I've been a senior software engineer at RudderStack for the past 5 years, and I've been working on systems which are backed by Postgres for the past 7 years. And yeah, so I've worked with this system very closely and very deeply. This is an open source system. All the code base which we work on is available to public, and I've made some of the fixes. I got paged in the night with issues, and we had to make some quick decisions to make systems work and then find out some real long-term fixes. And this is the work of an entire backend team over the past few years, and I'm here to present some of that. So a quick context of what we do as a company. So RudderStack is a customer data platform. So when I say customer data platform, it generally means that we help our customers collect data from their customers. So be it your mobile app or whenever you browse a website or anything of that sort, we collect data from that and we deliver that data to multiple third-party tools. So be it your databases like Postgres, Snowflake, be it tools like say Mixpanel, Amplitude, if you're aware of that, and be it message broking systems or whatever it is. So we do all of this, and if you look at this system closely, we can see that in the end, this is a giant queue which ingests events, transforms and delivers events, and all of this is based on PostgreSQL. Now the challenging part which we had here was that the 100K events did not belong to one single pipeline, and they belong to across 10,000 pipelines of different customers, and we had to ensure that one pipeline did not affect the other pipeline. So now coming to the question of why not Kafka. This is most asked question because the standard de facto system which handles such problems is a Kafka or a Pulsar as a message broker. But we did not choose Kafka for multiple reasons. So one of them is multi-tenancy isolation. So we are handling 10,000 pipelines and it's growing every day. Now if we wanted, so in Kafka the problem is you only read at the head of the queue and you need to pass from the head of the queue. But if we wanted to handle isolation at across these different pipelines, we needed individual topic for each of these pipelines, and it can grow out of bounds which any of the current message brokers cannot handle in the market. The next thing is, if we were able to club them into two, then we would have the head of the line problem where the top of the queue would block the events in the behind the queue. So if you look at Postgres, that would be much simpler to handle because it would just be a select star based on some metadata or some column, and we could just go to any row or any column in the queue, and we need not think about what's gonna happen over there. The second thing is complexity. So we were already running systems with Postgres, we were familiar with Postgres, but with Kafka we needed to introduce additional infrastructure, additional complexity with Zookeeper or the K-Raft which is used right now and everything. So this would introduce infra complexity, and we did not even have the expertise, or many people would not have the expertise to run a large scale message broker and not a Postgres system. And the third one is debugging. So in Kafka, if you have to find out which event is the one causing failures, it would be a pain because there is no SQL sort of interface, easy interface to sort of get data from Kafka and sort of help you understand what the problem is. But with Postgres, you can do a select star, you can inspect the data, you can update the rows, and everything would happen with just simple SQL query. So now I would just explain some architecture on how our data is, how we store the data. So we have two tables majorly, which we call a data set. So one is a jobs table and one is a job status table. So any event which we ingest from our customers is stored in the jobs table, and it's all an append-only data. And whenever we try to deliver a job, we insert two statuses for each job. One is when it is in progress and one when it is delivered. So for every job we have two statuses, and now these statuses can be succeeded, failure, to be retried, or whatever. Now again, the jobs table is not an infinite table. We have it fixed with each jobs table having only 100k rows, and whenever the cap is reached, we create a new data set. So we have data sets of 100k rows, and we have multiple of them. Now one of the problems would be that if your downstream tools are down, our statuses might just bloat up with just 10 retries. So imagine you have 100k jobs and the downstream tool is down. So, and I'm doing 10 retries, so you would end up with 2 million rows within a span of 2 seconds, and it just can bloat up at any point in time. But this is the thought I wanted to carry with on how the data set is structured. Now I'll just explain some of the problems which we had. So all the systems which I explained were working well, and once we hit scale, we started seeing these few issues. So query duration indexing. So we relied heavily on data which was fetched from index-only scans. But as the data grew and the complexity grew, and we saw a lot more problems, index-only scans were not possible. Like we had to hit the disk, and the query times which were around 20 ms started becoming 200 ms, 500 ms, and more. So we had to look into that and fix that. Next thing was we were doing an insert row by row, but that proved to be a massive overhead, and that was not working well with scale. And the table bloat problem I just explained about. Whenever the downstream tool was down and it was not a happy path, we had a sudden bloat in data, and the queries again started slowing down because we had to do some joins to get some data. The empty queue penalty. So I'll just explain this later, but yeah, whenever we had some queues which were empty, we were again hitting the database to know that, okay, there were no jobs. And this was an overkill on, this was an overhead on Postgres, since we already knew that that dataset did not have jobs. And yeah, there was also some issues with respect to the drivers we were using, which I'll talk about later. I'll just explain about each of the problem and what we did to fix it. So initially when we started the data set, we had this sort of indexes where we had an index on job ID and ID and job state, and this would help us read the exact data which we wanted from the status table. But we also had one more issue. So for every data set, we had data from multiple pipelines, and we also wanted to know what data was from each pipeline. So for that, we were initially doing something like select distinct pipeline ID from table where some column equal to this. So this was taking a lot of time, around 150 ms. Now we sort of wanted to optimize this, and we used a recursive CTE to sort of reduce this 145 ms to 1 ms. So what was that query? So this query is again very famous in the Postgres community, but this is sort of a loose index scan. This is not something which Postgres provides natively, but this is something which other databases provide, something like a MySQL or a Yugabyte or whatever it is, but Postgres does not provide this natively. But this is present in community where people sort of say that this is something which you can emulate this. So what does this do? So you have a recursive loop where I select the minimum of pipeline ID. So I select the whatever distinct columns I need from that table. I select the minimum of that, I get it. Then when I want the next one, I tell the query that, okay, find the one which is greater than this, the immediate one. So it uses only the index data to do that, and it will just jump to the next one, and it will not scan all the rows to understand if it's a distinct one or not. So, and we do this till we find a column which is null. So when it is null, we know that we have all the entries from this data set which are distinct, and this sort of query is much faster, as you can see from the previous slide, around 150 times faster than what we were doing earlier, and the regular distinct column ID. So this sort of helped us speed up some of the queries, and we were able to again achieve the numbers we were able to do right now. The second thing was that we were initially using an insert query to push data into the database, but this insert query was very slow, and Postgres had a lot of overhead when it was trying to do an insert row by row. So the solution which is here is, I think most of you must be knowing, is the copy command, which helps insert data in bulk and not row by row, and it eliminates that overhead which we have in a row by row sort of insert, and this helped us become more performant. So when we have to build high throughput queues, bulk loading is a mandate and it's not optional. We need to do this no matter what. The third one is how do we handle the retry storm. So when I mean the retry storm, whenever the downstream destination is down, we sort of retry the data again and again to be able to deliver that data. Now, within few minutes or few seconds, the tables might throw out of bounds, and when we try to find the jobs which needs to be sent, it might be the case that the joins take a lot of time because it has to join across a table which has millions of entries, and this would increase the query times. So the first approach which we did was we tried to compact by pausing all the reads and writes and copying the latest statuses to the new table and doing this sort of thing. But this was not optimal because this might take a lot of time where we have to sort of stop all the processing, and we end up having some processing downtime before we reach a state where the queries are manageable. So then we sort of broke it down into two things. Whenever the data set is complete, instead of deleting the data, we just drop the data set. Deleting the data would mean that you would have to again clear the tuples. When you delete the data, tuples are not immediately removed. So when you drop the table, all of them are removed and it's much cleaner, and Postgres stats are much aligned. And for active data sets, what we did was whenever we had multiple data sets with small number of jobs, we sort of merged all of them into one data set. So one thing which we observed was having a large number of tables would mean that there is a lot more overhead in terms of metadata and everything to have it in your columns, for Postgres stats, and this generally means that you would have to, the queries would take much longer because it has to accumulate data over a lot of stats and it has to return data. But when you merge these and have one table and sort of do vacuum analyze, the planner is able to adjust its stats internally, and it provides with a optimal query plan so that the queries are faster and it uses the index better. So I think the key takeaway here is that drop table is much better than delete plus vacuum. And the next thing is that conditional merge. So when we have multiple data sets with 10 jobs, 10% of the jobs, we read these jobs and create a new table and copy all these jobs there. Then we drop the original 3 data sets. So we don't delete from these, we rather copy them into a new data set and drop this so that the stats are aligned. This is an automated loop cron job sort of thing, which always checks every 30 seconds to see if you have such data sets. So when we process data, we also have to process in order. So we process from the data set with lower number to data set with higher number. So whenever we do that, we have a cron job which checks from the head of the queue to see if there are such sparse data sets, and we have a definition for sparse data set, 10% of the jobs, or you have a large status table with so many dead entries or something like that. And yeah, so and whenever such rules are aligned, we sort of try to make it into a data set which is complete, which is like 100k rows, which is a complete data set according to us. So we try to have as many less tables as we want, and this compaction happens runtime, so we do not do it manually. Yeah, so yeah, it is. So we ensure it by having application level logs. So we have some sort of mutexes on application which, yeah, but again the copy plus delete is much faster than the earlier deletes which we did. Copy plus drop is much faster, so it was not that the downtime was not much, and yeah. So everything, there's a trade-off with everything, and you cannot do everything with zero downtime. So the only thing which we tried was to optimize the things which we were doing to get to a place where we were able to handle the traffic which we had. So yeah, the next thing was the empty queue penalty. Now, as I already mentioned that we had 10,000 different pipelines, and each of the data set can have data from any of these pipelines. Now, all the 10,000 pipelines are not active at every point in time. There are only some pipelines which are active, but we don't know which pipeline is active and which pipeline is not. So we have to make a database call to understand if the pipeline is active or not. And if that's not active, we need to sort of discard it. So the problem is, for the same data set, we don't know if the pipeline is active or not unless we query it. So these queries which result in empty output were causing an overhead in terms of QPS. Postgres had to hit the disk and see if it has data or not, and it has to respond. So this was degrading our performance. So we had an application level cache where we say that, okay, for this data set, these are the pipelines which are active. So after we hit the 100K rows, the data set is complete. We are sure that there is no new row which is entered into that data set. So we know what are the pipelines which are active in that data set, what is done, what is not done, and everything of that sort. So we have a cache for every completed data set saying that, okay, these are the data which is active. Now, if you have a pipeline which is in this, go and query. If it's not in this, you can just return an empty response, and we need not hit the database. And even in the even if a pipeline has jobs, we need to know if it has active jobs or not. So we again make a query. If we get returned with no response, no jobs as a response, we then cache it so that whenever we do this again, we do not have to repeat this. So the key takeaway here is that we do not want to hit Postgres whenever there is empty result. So we do not want to burden it with unnecessary queries where we know that, okay, there is no output which is going to come. And if we know it already, we need to have we need to have it stored somewhere so that the performance is optimal. And this eliminated more than 95% of the queries, and the number of queries which we made to database were very low, and the IOPS and everything also sort of reduced. Yeah, this is one interesting thing which we found. So we were trying to store the data which we were getting into the database, and we were using the driver which was Go driver, and we used the standard Go library to insert the data. Now the thing which we observed was that there are types like so we have a JSON data, and with an insert in types in the type of a byte array or as a string into the table. So imagine that you have a text column on Postgres. So Go provided two semantics, one as a byte array and one as a string. So what we observed was that whenever we were getting X amount of data as input, we were writing 2X amount of data to Postgres. And this we realized by seeing the network graphs of input and output. And when we did deep into this, we realized that, okay, whenever we are using byte array, the library which we were using was doing the hex encoding, which was doubling the size of it, and we were writing more data into it. And when we moved it to string, it was just half of it. So it was using the exact thing and passing it as raw bytes to the database. Now the underlying point which I want to make here is that even though we might be assuming that we are writing whatever we want, but all of us depend on some sort of ORM or some sort of library which does things in its own unique way, and we need to keep a check in such systems where we need high throughput to see if we are losing something which is very native. Like we had a lot of network tasks and so much egress and passing so much data also took a lot of time, and this simple optimization of byte to string just saved our query time by half. Like because we were passing lesser data to Postgres, it was able to write it quickly. So this is the takeaway here, that we need to understand what the ORM or the library which we use sort of does underneath. How does it implement the data transfer to Postgres, and what sort of tips and tricks are present in that, so that we get the best use of it. And yeah, so one other thing is that the reality is whenever we want to write 1 MB onto Postgres, it will end up being 3 MB when you actually write it on the disk. So you will need to first write it to a val, you need to do a page write, you need to update the indexes, you need to and if the payload is much larger, you need to also update the toast tables. So even if you assume that your IOPS, I mean the ingress and egress are say 100 Mbps, your Postgres might get throttled because it might need more write-in data. So it might need 300 Mbps to write. So we also need to factor in these sort of conditions where we need to see what all data is actually being written to Postgres and how much IOPS are needed for that and how much throughput is needed for the Postgres which we provision, so that it's able to write all of this properly without being throttled on these aspects. Yeah, the next thing is, in the initial days, all of your data was present in shared buffers, and whenever your data is present in shared buffers, the query gets fast, like you just get results instantaneously. But once the data grows beyond a size where it does not fit in the shared buffers and it exceeds your RAM, Postgres sort of optimizes the system in a way that, okay, it tries to fit everything in its RAM and tries to return results from the RAM. But once it crosses that, it sort of has this IO bottleneck, and you have unexpected performance that query times are not something which you can predict. Like it becomes unpredictable. You see spikes, you see lows, highs, and everything. So we need to test with systems where our database size is much higher than what RAM we provisioned to be able to understand how the query patterns would be and how does it behave under stress and how optimally it's able to use the RAM and indexes and everything in such cases. And yeah, so IOPS, RAM are something very important. And the last thing which we did was, so we were also trying to understand what would be the best, and all of this which I explained earlier are from mostly an application level and from query patterns, but now we also try to tune the PostgreSQL conf to see what sort of configuration would fit our workload better, and we came up with these. So the auto vacuum nap time, we reduced it so that the vacuum becomes faster, and since we drop a lot of data and we don't store any data, we wanted the tuples to be eliminated as and when they can be. And with an SSD, we wanted it to prefer index scans over sequential scans. Postgres has this tendency to prefer sequential scans if it feels that the index is not that useful, but we wanted it to prefer index scans because we were confident index scans would be much faster. And with SSDs, we went with this random page cost of 1.1. And we also wanted frequent checkpoint because we could not afford downtime, and since we were a real-time system, whenever Postgres restarted, we did not want to afford any downtime of more than 1 minute for the Postgres to be able to come up, because it has to do a lot of stuff when it has to restart, and we did not want to afford that. So we want to checkpoint as fast as we can. We also increased the max wall size to 2 GB and wall buffer 64 MB. And again, this is the configuration which worked for us, and we have been using this since the past 1.5 years. But any configuration changes with respect to PostgreSQL should be tested before, and should be thoroughly tested before you move it to production. So yeah, a summary of all the lessons which we learned would be that we need to index aggressively and also need to understand how much can we extract from our indexes, and we can use recursive CTEs for loose index scans, which Postgres does not provide. We need to fight the bloat. We need to be able to compact, and we need to drop over deletes. Deletes are much bad on Postgres, and if at all it's possible, we should be able to drop. We need to watch the wire, like we need to understand what our ORMs or any driver which you use does. We need to avoid the queries which sort of return empty results and do not provide any meaningful impact for our application. We need to avoid as many queries as we can to the database if our application is able to handle it. And copy is mandatory. I don't think we can. We need to do an insert when we are doing the bulk load. So yeah, we have a blog written on the same with much more detail. So you can scan this QR code for the blog. And